you feeling today? A lot of pressure on your shoulders?
Oh man, that's a lot of pressure.
You all feel pressure.
Now we're talking about pressure today, and gases produce pressure. And so, but here's kind of the weird deal. The gas molecules are moving crazy fast.
Yeah.
Crazy fast, like actually about 1,000 miles an hour.
Have you ever been hit by something going 1,000 miles an hour? Aside from gas particles?
Not really, no.
How about you guys?
It would hurt.
How'd that work out?
Not very well.
No.
So when things are moving 1,000 miles per hour, but there's some reason, why am I standing here and not being hurt? And why are you sitting while you're watching this getting hit by 1,000 mile per hour molecules? And the answer is they're really small.
Mm-hmm.
And so the force added together you'd think was not that high.
The reality is that we'd be fooling ourselves if we're like, but they're so small they don't impact us. The force we feel on us is actually pretty crazy. Can you give us an example of that?
So here we are living on the planet Earth. And on the planet Earth,
Most of us.
Most of us are, yes. You're not going to believe this, but if you, make a box that's 1 inch by 1 inch by 1 inch.
And just to make it clear, he made one by 3 inches here, just to make it
just looking larger. But it's 1 inch, which is like 2 fingernail widths. And you know what the pressure is right now? If you're at sea level, it's 32 pounds for every inch squared. That's crazy. So imagine that I were to put a 32-pound weight. All right, go to the gym and get a 32-pound weight. That would be a small, really heavy weight. And put it in every part of your body, 32 pounds. It would crush you. But wait, that's the pressure we're experiencing right now.
Yeah, I'm old school, and you know how I love to deal with Animal Planet type stuff. I've heard the analogy that the pressure we feel on us all over our entire body is as if a smallish to medium-sized elephant is stepping all over us. Now, I don't know when the last time you were stepped on by an elephant was.
Not recently, no.
No, and all of us here are probably thinking the same thing. Okay, Mr. Bergman, Mr. Mitrich, how is it therefore that we are not getting crushed? Because if we went to the gym and we said, hey, you know what? Put all those weights all over our body, we'd have a bad day, wouldn't we?
It would kill you.
So I always do this with my students. It would be a play-at-home activity. Just take your finger and the tip of your finger and just push in on it. Yeah? So when you do that, you see that the idea is that
it's white.
You have, I have blood. We have blood that courses through all of our body. And the reality is the reason that we don't get crushed in is because we have equal pressure pushing out, which is kind of the topic of today, where we say that anytime you have two forces that are pushing against each other, they cancel each other out.
That's right.
So we all would agree that we're breathing in air that is equal pressure to the outside. Is that fair?
So those air particles, like in my lungs, are pushing out with the same pressure that the air
outside is pushing in.
So they balance each other out.
Yeah, so that 32 pounds on the outside pushing in, we have that same pushing out. Now, if that was only our lungs, we'd be having a bad day, but you realize that, and not to complicate this, but biology is super cool. You breathe, and those oxygen molecules hop onto some hemoglobins. They go down to the very tips of the arterioles in your fingers. So every single part of us has that same pressurized feel that the outside does. But let me ask you this question, and let me ask you guys this question. Yeah, it's all great when two pressures are equal, but what if one pressure is greater than another pressure?
Well, the pressures will try to equalize.
Yeah, so if you have, and let's talk in terms of gas molecules, right? Let's say you have a great deal of pressure, like gas particles that have a huge amount of pressure, and then you have somewhere else where there's not very much pressure. Gas particles will always try to go to where there is less
So I
pressure.
got like an empty place where there's low pressure, and here I got lots of gas particles, and I open up a hole right here.
Oh man, this is gonna be crazy, slamming into each other trying to get across.
So this happened to me the other day. I was riding my bicycle home from school, and all of a sudden I heard this sound, and I thought, bummer, my date's not longer.
That's never a good sound.
Because I hit a nail and I popped a tire, right? So the high pressure bicycle tire was trying to go to the low pressure atmosphere, and then I lost all my pressure in my tire. I had to replace my tire tube thing. So this is basically the idea, right? I popped the hole and then it popped out. Now, in reality, what happened to my bicycle, there were gas particles here, but there were a lot more here, and then they zipped out. Now, there's lots of other interesting applications of this idea of pressure.
Yeah, I mean, I don't know what our scuba diving population is here or how many guys are like parachuters or whatnot, but we experience this all the time just with how we're moving around. For the higher up you go, the thinner, less particles of gas there are. That means simply this. If I have, and you've been in a plane before, right? When you open a plane, you hear yours pop a little bit, right?
Yeah.
But the reality is that they're pressurizing it, trying to keep the same pressure on the inside as you had on Earth, right? Or on the ground. Now, How many of you guys would feel comfortable when you're flying at 700 miles an hour at 40,000 feet, have someone open up one of the doors? How would that work out for all of us?
We would die.
It would not be a very, and that happens occasionally. It's not a great thing. What ends up happening though is kind of weird, because when you have a plane that's flying, inside you have pressurized particles. On the outside, as you go up higher, there's less and less particles, and whenever you move quickly through something, I don't know if you know this, the pressure on the outside becomes less. So, as we're doing this, if you have an opening, all the gas particles on the inside, and you're like, oh, less pressure, go, 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 go. And the reality is when we talk about something getting sucked out, that's not really happening. The gas particles push things out with them in their and if that happens to be you, you have a bad day. And in fact, I love this expression. What did we say about chemistry?
So guys, everybody repeat after me. Chemistry
never
sucks.
Never sucks.
It never sucks. In fact, here's another example. We've always used the term, I'm sucking in my milkshake, right? So you got a straw, you got a milkshake, chocolate.
Clearly. Or Oreo. Let's not be biased here, right?
All right, and you have your mouth, you put your mouth over it, that's your mouth.
It's anatomical. That's beautiful. That's beautiful.
And what you do is you create a place of low pressure here. And then what actually is happening is that the air pressure from outside pushes down on the milkshake and it pushes it up into your mouth. So you actually never suck on a milkshake.
By the way,
you create a low pressure area and the atmosphere pushes it in.
now gas isn't stupid, right? So have you ever had this experience where a little slit in the straw occurs? So if I'm gas particles, and there's tons of them here, and they're very angry gas particles, right? And they're all trying to get in to where you've created low pressure in here, right? They're like, well, I can push down and try and go up the liquid, which is how a straw should work. Or if you crack the straw, it's gonna be like, thump.
Yeah.
And I don't know if you've experienced that before, and who hasn't, right? It's gonna be a bad day for you. Know this, particles of gas, and anytime you have higher pressure, it goes from high to low.
So high to low. So just write that down. Always go from high to low. So another example is, let's say that one of you is a junior high school girl. Pretend that you've done this when you were a junior high girl, you know this, and you had first started to experience perfume. What did you do? You probably overdid it. Boys, maybe it's aftershave lotion or whatever. And when you walked into that junior high school room, everybody knew that you had just experimented with perfume for the first time, because the gases act independently. So what happens is there's this high pressure of gases coming off of you, and they have an odor, and all of a sudden it starts to expand through the low pressure room and into everybody's nostrils, and they go, someone's wearing perfume.
And the reality is that this happens across the board. Like simple things like back in the olden days, it was cool to smoke. Like that was a cool thing. Like you had a cigarette or a cigar. Well, we didn't have cigars, and I didn't do this, but other children did. But you'd be in a car and you're like, let me relate to you guys. You know when you're vaping and you're super cool, right? And you're in a car and you crack the window open, what happens to the vapiness?
It goes out because it
goes
high pressure
out
to low pressure.
Right, and because that must mean that inside the car we have high pressure and outside the car we have lower pressure. Now there's also something, I think you shot a video a while back on...
Yeah, let's talk about how high pressure to low pressure as it relates to altitude. Now one piece of background information, as many of you know, I used to live in the mountains of Colorado, and you said this earlier about the airplanes, Mr. Dmitrievich, but when you are at sea level, you have a certain amount, it's 32 pounds per square inch or whatever, right? But when you go up at higher elevations, it's less. And so I used to live at 9,000 feet. And at 9,000 feet, the pressure was about 75%. So whatever 75% of 32. But then I actually went way above 9,000 feet in this video. Let's take a look. Here I am at the base of Mount Evans. Now if you look back up here, you're going to see a bunch of mountains, and I'm about to climb that mountain here. But I have myself a bag of Pringles Minis, and I want you to notice the bag's kind of roughly like this, or you can push it down. It feels a little full probably compared to what you're probably used to if you live at sea level. But think of the gas particles striking this all of a sudden. But we're about to climb on our bicycles the highest paved road in America, which is the Mount Evans Road, and we're going to see what this bag looks like, and it's actually an application of Boyle's Law. So we'll see you there in a few minutes, or hours. Rolling. And we're on the highest paved road in North America. Pikes Peak Highway, riding up. Mr. Creekshauser, what altitude do you think we're at?
We're right around 12,000 feet.
12,000 feet. So, now look at my Pringles potato chip bag. Now compared to what we saw, it's totally full. Boyle's Law in action. How's that Boyle's Law? Well, you see the gas inside, the pressure is the same. I'm breathing hard. The pressure is the same, but the external pressure at this high altitude is lower, and therefore the molecules, here I'll try and show this. Here, let's pause here. The molecules that are hitting this, well, there's fewer of them because we're at a higher altitude. But the molecules on the inside, the air molecules on the inside, they're the same number. Therefore, the bag expands. Now, we're going up there to the top of Mount Evans, 14,200 feet, I think. When we get there, I anticipate that this bag will be either fuller or possibly it will explode in my backpack and I'll have a mess. Let's see it. I'm at the top of Mount Evans. It's a windy day, and I got my bag of Pringles Minis. Look at how big that is. Totally full. I think it looks, because of the Boyle's Law, not very much air up here, even though it's windy, so it caused the potato chip bag to expand. You know what I ought to do? I should eat some. And so as you can see at the top of the mountain, and I use the term Boyle's Law in the video, and we're going to talk about what that actually means a little bit. But you know, the potato chip bag looks like this at the bottom, and at the top it's completely full because of that pressure differential.
So what if we go the opposite way? I mean, we just saw Mr. Bergman going up with a potato chip bag, and that's delightful. Congratulations, by the way, on making that far up. But what if you go down? The farther you go down, the more pressure you feel. And when you can't go any farther down on the earth than if you go into, let's say, an ocean or a lake or down into water. And one of the things we know about water is that water actually creates more pressure than air even does. So one of the fears that you'll be able to have, I've had in my life, I'm going to share with you now, is what if you're in a car and let's say you're a teenager at any school, right? And you happen to veer off the road and end up in the water. What should you do? And is it important that you act quickly?
Well, let's think of this through, right? The problem is pressure. So when you go down underwater, now you have a high external pressure compared to the low internal pressure of the gases in the car. And we've been talking about gas pressure, but pressure is pressure.
Yeah.
And water has much more pressure than gas because it's much more thick, I guess you could probably say.
Yeah. So
the problem that happens is as your car is sinking in the water is you're not going to be able to open your door because the pressure is going to be so intense that you can't get out.
Yeah.
So how do you solve
What
that?
about your window? Can you open your window? What if you roll it down?
Well, will it allow itself to roll down? Probably the electricity has killed if you've got a powered window. Maybe you've got a roll-up window. Very few people do, though.
Well, let's transfer back to the 70s. What's kind of crazy about this, and I don't want to spoil too much on the videos that we're going to watch in class, the pressure you feel is so strong that even if you had the ability and the strength to roll it down or an electric window to pull it down, there's no way to even roll the window down. And they did studies where the power for some reason will still go even when you're underwater, but the force is too great. So the idea of like, hey, I'm just going to open up the window.
Because you have to equalize the pressure.
Yeah.
This is the key. You have to equalize the pressure. You've got to get out. Obviously, if this car is down here and you've got a lot further to swim up, that can be bad. So you want to get out ASAP. And the only way to do it is to allow the pressures to equalize, which means you have to do what?
Break the window.
You have to break the window.
And
they sell these things that are like window breaker things. Put them in your glove box. If you don't have one, I would encourage you to buy one. Put it in your glove box of your car, and then it will crack the window, and then allow the water to equalize, and then get the heck out of the car.
Yeah. And mind you, we think, well, wait a second, we're not going to be driving to the ocean. But we're in Houston right now, right?
Yeah.
Let's be candid. We've had hurricanes, and I've been floating down my street.
So, and there's other interesting applications with like a scuba diver.
Yeah, I know that some of you guys probably are even taking scuba classes and whatnot, and the same thing applies. I always ask my scuba kids what instruction they give you, and they say this: when you're going down and up, you breathe, which seems really, really weird. But if you think about it, your tank is actually pressurizing your internal with what the external is. Remember, you always want to have the same pressure, because if the pressure goes either direction, you're having a bad day. So if you take a breath, that's delightful. If you take a breath, and he's at the surface here, but let's say you go all the way down to here, and you breathe all the way down, everything's great. And then you're like, ooh, pretty, and you see something up above, and you take a gulp of air, and then you just bloop, 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 swim up without equalizing your pressure.
So then what's going to happen is the air that you've held in your lungs are going to want to expand, and for
Yeah.
every like 10 feet, it doubles or something like
Yeah,
that.
it's crazy. that-
And so it will actually kind of blow your lungs out. You won't be able to actually do it. Your lungs will just be pushed, and the air will expel. If you try to do this, you can get a condition called the bends, and it's just very bad.
Yeah, it's not just your lungs that want to get out. Every single molecule of gas you have in your blood and everything. So and gases aren't stupid. They want to go through the easiest way. So like the bursa sacs in your elbows and joints,
Very, very
which is
painful.
why you bend over. We're going to explore this a little bit more, and we're going to watch a couple of videos on this as well. But man, this is a cool subject, right?
Last topic, interesting. So let's pretend you're an astronaut, and you're an astronaut, and you want you're going to go work outside. You put your whole spacesuit on, and you go do your mechanical work that you have to do, and then you say, "Hey, I forgot my hammer. It's out there, my wrench." And you think,
We've all been there, right? In space,
and
we
you-
got our hammer.
and you go, man. So, but I was a swimmer in high school. I could hold my breath. I could swim 2 laps underwater. I can do this. And I got good warm clothes on. I know it's a little cold out in space. And so what I do is I open the airlock and I hold my breath. And what happens?
You had a really bad day really quick. Pretty much every part of you that's inside, remember, you're pressurized. Outside, there is no pressure. So what's going to happen to those products on the
Well,
inside?
think of my eyeballs are like these little sacks of gases. They will just, boom, explode. Really.
Yeah.
It would be ugly. And every cell in my body is going to want to do this, and it would all be bad because you're going, pressure wants to go from.
High to low.
Is there any theme today?
Yeah.
Is
So,
what?
yeah. By the way, what your takeaway is this: when you're in a space station, boys and girls, leave the hammer outside until you're properly dressed. That's really what our takeaway is from this, right? You guys.
High pressure to low pressure.
High pressure to low pressure. We look forward to seeing you.
Bye.
Bye.